Hi guys, this is lesson 7.7, Exponential Growth and Decay. You should have your notes ready, and you should have noted the key concepts on page 460. If not, pause the video, do that, and come back. Alright, the thing that I want to show you from this key concept that you just noted is, first of all, that this A value, this function should look familiar to you, right? We just learned this in a previous lesson. This is an exponential function. We're going to learn how to model growth and decay. Growth means something gets bigger. Decay means it's getting smaller. All right, so A always represents the initial amount, whatever we started with. Okay, our initial amount or our starting point, what we started with. B stands for the base. If this is a positive number, we will have growth. If it's a negative number, we will have decay. So positive equals growth, and negative equals decay. Alright, and x is our exponent, and it's a variable. So our variable exponent. Alright, now that we've talked about that, you will find this to be very similar to lesson 7.6 where we worked with exponential functions, only now we'll have more purpose for them, some real life situations. Pause the video and read the word problem for problem 1, and be ready to come back and label these variables. Alright, when we look at this problem right away, we probably remember x and y. X is independent, y is dependent. And the two real variables here that we're dealing with are years, which is time, and money. And we know that time is completely independent. The only one who could ever affect time is God, that money cannot change time. But time has a definite impact on money, especially in this problem that's asking us about a trend of money being spent in restaurants. Alright, so then we just have to think about A and B. And we know A is always our initial amount and B is always our rate. So let's look at this. We're going to do Y. And then A, our initial amount, was $360 billion. We can just write 360 and we could just note that A is the money in billions. And then B is our rate. And since this is growth, we're going to do 1 plus our rate. If it was decay, we would do 1 minus our rate. Alright, and 7% as a decimal, we know we move the decimal 2 places to the left. So that is 0.07. And this goes to the x power. Alright, and so then we can go ahead and simplify that y equals 360 times 1.07 to the x power. I suppose I didn't need parentheses there. We could just write the multiplication symbol instead. Alright, then we want to think about what the problem's asking us for. It wants us to predict the year 2015. And we started this whole thing in the year 2005. Our x actually represents time in years after the year 2005. So we're going to go ahead and subtract that, and we realize we're looking at a 10-year period. So we're going to put 10 in for x. So y equals 360 times 1.07 to the 10th power. We're going to type that into our calculators, and we're going to get 708. And think about what that answer is. This isn't 708 years. This is $708 billion spent at restaurants in the year 2015 if that trend continued. Alright, let's look at B. B wants us to express this in the form of r to the m so that we can have the equivalent monthly increase of spending. So instead of spending 708 billions per year, how much are people spending in a month? And the way that we do that is we have our 1.07 to the x that we were thinking about before. And since there are 12 months in a year, we could think of this as, so here is a year, right? 12 months in a year, and then our x here. So if we want 1 month, that means 1/12. So 1/12. And we're going to have that go to the 12x power, right? This is the same thing as what I have above, right? If I distributed, I would have the same thing. But now this gives us a chance to think about it. And so we're going to put this part into our calculator. And when you calculate 1.07 to the 1/12th power, don't forget to put this little guy in parentheses to make that work, we will get 1.0057. And then that will still be to the 12x power. And since 12x represented months, we can just go ahead and write that as 1.0057 to the m. Alright, pause the video and do got it 1 and come back. For got it 1, you should have gotten about 43,872 subscribers, and when you represent it as monthly, it would be 1.05 to the m power. Alright, let's go ahead and get ready for problem 2. This formula is a formula that is used for many years in people's lives. And this is the compound interest formula. This is used on bank accounts, credit cards, and savings, all kinds of things. So it's important to know what these variables represent. And A represents the balance of the account. This could be, if it's in your savings account, this is how much money you have. If it's your credit card account, it's how much money you owe. Alright, so this is the balance. Or if you like, because it starts with an A, you can call it amount, but you need to remember this is the amount either you have or the amount you owe. P stands for the principal. That one's not quite as easy to remember, so just think of it, this is your initial amount. So it's the amount that you either deposited into the bank account if you're trying to get interest, or it's the amount that you've borrowed if you're paying somebody else interest. R is your rate. And make sure to always put this in decimal form, okay? Don't leave it as a percent, which is what you'll probably see it as in a problem. Write it in decimal form. N is the number of times per year that the interest is accrued, or compounded, I'm sorry. So the number of times per year that interest is compounded. And again, I'm sorry about my handwriting with the stylus. And lastly, T is time in years. Alright, we're going to go ahead and put that to work in problem 2. Problem 2 asks us, it says, suppose that when your friend was born, your friend's parents deposited $2,000 into an account that paid 4.5% interest compounded quarterly. That means 4 times per year. What is the account balance, what will it be when the child turns 18? So you just have to think about which variables to replace, just like with any word problem. P represents the initial amount, so that's the amount that we started with, the amount that got deposited. 1 is just always going to be 1. Then we have to think about our rate in decimal form. It's 4.5%. If we want to write that as a decimal, we need to move this 2 places because percent means out of 100. So then we have 0.045. Since the interest is compounded quarterly, we have a 4 here and here, and we want it for 18 years. And then we just follow the order of operations and find our balance, which ends up being $4,475.53. Go ahead and pause the video, do got it 2, and come back. For got it 2, you should have gotten $4,489.01. Good job. Now let's look at decay. Problem 3 has us modeling exponential decay. Go ahead and pause the video, read the problem, and come back. Alright, so all we have to do is think about what our variables represent. And we need to think about the altitude and the atmospheric pressure, which one depends on the other. The altitude isn't going to change, but based on where you are with the altitude, the atmospheric pressure will change. So x needs to be the altitude and y needs to be the atmosphere in order for the dependent and independent to work properly. So we know that y and x are going to stay in the same position. We need to think about what a is. And remember that a is always our initial amount. So this is our initial pressure. And given in the problem, that is 101. Then our b is our decay factor, growth factor or decay factor, right? This is telling us it decreases, so that means it's decay. We were given 11.5%. And we know to change that to a decimal, we move 2 places. So we have 0.11, oops, why am I making that up there? This isn't a compound interest problem. 0.115 to the x power. Oops, I forgot something important. Remember before when we did 1 plus? Because this is decay, we're actually going to have 1 minus 0.115. There we go. And that goes to the x power. It wants us to say what the approximate pressure is at 3,000 meters. And so I don't really want 3,000 as my exponent up here. So what if we have x represent the altitude in thousands of meters, and we can just go ahead and put a 3 there. And then we'll just have to remember that when we go to write our answer, what that means. Alright, so we'll put a 3 there, so 101 times, let's go ahead and simplify this inside. 1 minus 0.115 is 0.885, and we'll have that go to the 3rd power. We'll use our calculators and round this to 70, and then we just have to think about what 70 means. So the pressure at an altitude of 3,000 meters is about 70 kilopascals. Alright, go ahead and pause the video and do got it 3. You should have gotten about 55 kilopascals. And for B, if you did it, the decimal equivalent of 100% is 1. Alright, your to try problems are the lesson check problems. Go ahead and do problems 1 through 5. So try lesson check 1 through 5, and then come to class ready to ask me your questions.